Pawsey sits on the Whadjuk country of the Noongar Nation, and we'd like to pay our respects to their elders past, present and emerging.
The swimming changed my personality, made me channel that energy into challenges and things like that. So you're always striving to be better and things like that. And that mindset is basically put me along the whole career.
What does swimming and supercomputing have in common? Welcome to HPC Hearts and Minds, where we talk to the people behind some of today's most fascinating discoveries. High-performance computing, or HPC, allows researchers to tackle incredibly complex questions. This series is all about finding out what can be done using this kind of large-scale tech. More importantly, it's the hearts and minds behind that tech that make it special. We've been lucky enough to speak with a handful of amazing people for this show. First on our list is Professor Charitha Pattiaratchi, an oceanographer at the University of Western Australia. For over 25 years, Chari has been instrumental in showcasing the power behind the waters that surround us, including discoveries in tsunami impacts and dense shelf water transport. Chari received the People's Choice Award at the Premier's Scientist of the Year for 2025 for his contributions to Australian oceanography. His work has also helped discover locations of debris from the missing MH370 flight back in 2014, which we talk about as well. Chari sees what he does as if it's a jigsaw puzzle, taking each piece, like supercomputing, fieldwork and satellite imagery, and putting it together to see the whole picture. Studying the Indian Ocean and why it vastly differs from other oceans. Chari, thank you so much for joining me today.
You're welcome. Yeah.
So what got you into oceanography before you got into it?
Interesting. So I wanted to be an oceanographer from the time I was 13 or 14.
Oh, right.
My father was a geologist, and then so we had, the family had science background, and I used to go on field trips with him around Sri Lanka, and I got interested in science and things like that. And then I also started swimming. I was reading in those days, of course, that age group, you always read comics, not Marvel superheroes, but funny ones. And I saw this little piece on this comic which says, a career in oceanography. An oceanographer basically studies the ocean. And there's different components for oceanography. So there's physical oceanography, which I do, which looks at the physics of the ocean. So waves, currents, tsunamis, how the ocean works, how the ocean moves. There's mixing. So that's a physical oceanographer. Then there's a biological oceanographer, which looks like what happens in the biology of the ocean. There's chemical oceanographers. There's geological oceanographers. So, every single part of the ocean is studied by different groups. So it's a multidisciplinary area. So I build the instrument. I do all the electronics, I do everything, and then I take the student out on a boat, I drive the boat, we collect the data, and then we download the data, then I write the MATLAB scripts to actually analyze the data. So from a drawing in a piece of paper, this is the instrument that I want, all the way to actually writing a paper. That's the whole stage that you go through. Lots of the things that I did was basically because of the team that I had, fantastic students, fantastic staff, to be able to do that.
I guess it's really hard when you have to explain that to somebody because there are so many factors that lead into what makes an ocean, really, essentially.
Yep. So I said, hang on, this is something for me. And interestingly, I wrote it down in a little blue book, and I still got the blue book. And when I read it, I actually say, hang on, this is what it said 13 years ago, what you would do in an oceanographer. And I look back and say, hang on a minute, I've done all of that.
That would have been so great at 13 years of age, because I know a lot of the times when you're that age, you have no clue about what you want to go into.
But it was a little bit forceful as well, because I wanted to become a geologist.
Oh, right.
But my mother said, no, I'm not going to have two people with the same profession in the family, because my father's family are basically professional musicians. And whenever they got together, they would argue. So she says, look, your father's family? Nope, that's not what I want in my family. So you're not becoming a geologist.
I mean, that's such a strange profession as well to be banned from. It's like usually it's an artist or an actor, like no family is never going to go into those kind of fields. But I mean, oceanography, or at least, science and physics and these sorts of things are still, I mean, as a geologist, I'm sure your dad has many ideas.
The interesting thing is, now I keep, people asking me, said, what do you think? Sri Lanka is an island nation and things like that. But I actually tell people, what do the general population of Sri Lanka think about the ocean? Right? In one word, scared.
Right.
People are really scared about the ocean. So this is an interesting part for me as well, because, I was Sri Lanka's best swimmer.
Right.
But my father would not allow me to go to swim in the ocean. He was too scared.
Right.
You can swim in the pool, not in the ocean. So he also had a problem in terms of me becoming an oceanographer, going out in boats and doing things. So he had to come over it when I actually started studying. I remember he came and visited me while I was studying, and I said, I'm going on the ship, and you could see his expression change. He was good to support to become an oceanographer, but I don't think he really realized what it entailed.
It's too bad you couldn't say, study rivers and streams, please stay away from the oceans. What I find really fascinating, the fact that, because you were a professional swimmer and had a lot of high quality titles for a long, long time, right, in Sri Lanka?
Yeah, and also when I was at university, the time that I was an undergraduate, I was the fastest swimmer in English and Welsh universities.
Not a bad title to have, I think. Do you feel like the love for the ocean helped you in terms of swimming as well? Do you think they both went hand in hand at one point?
No, they're sort of two different things. But, when I was born, I was very sick. My life expectancy was 2 years.
Really?
Okay. So very sick child and things like that. So, and one of the part of that was that I actually did not speak or communicate till I actually started going to school.
Wow, okay.
Right. So that was, and then while in school, I was basically hyperactive. So going from one to another and whatever. The thing is that the swimming changed my personality and whatever, but also it made, of course that ADHD and whatever, athletics and all of that, made you a competitive person. But swimming made me channel that energy into challenges and things like that. So you're always striving to be better and things like that. And that mindset is basically put me along the whole career. You basically have to be best, and you want to, and do the best you can. Right? So that's the sort of the training that actually got into it. So a few years ago, I did the Rodney swim because that was a challenge.
Right.
Because for 20 years, I have been predicting the weather and which way the currents are going and things like that. And I said, okay, maybe this is something I should do. I always wanted to do it, but never had the opportunity. But then you do it. So there are different challenges that you want to do, and day to day.
It's a beautiful thought to think that something like a sport, like swimming, for example, can have a really good place in the fields of science and study and research, because you are, in a sense, having a bit of a challenge in whether it be a distance or endurance for sport, but then, trying to find really scientific challenges. You're either swimming in a vast ocean and trying to find a very, very small, minute thing, but that, with hard work and persistence, you'll hopefully find answers. So it's the same kind of, I guess, drive.
But it's the mindset, right? I mean, so, in swimming, you set a goal and, you want to do, okay, here's the record that you want to break. So you actually then, but it's not only that you have a goal, you also have a plan to achieve that goal. How you train, how you do, all of that is stepped in your mind, you do it. Sometimes you actually don't even think you're doing it, right? But that's why you go and train. That's why you spend 6 hours in a pool going up and down a black line, right? And the most boring thing you can do, but you're trying to strive that. You're concentrating, you have perseverance, you got determination. So when you actually come, in the same way, we're talking about computing, right? You're writing a code, You want to get that code right. You want to get that code to be able to do what you want it to do, right? It's the same analogy. You persevere. You actually say, I want that. And you actually keep going. So you can see it's the same mindset.
Yeah. It's a great, I guess, lesson to be able to take into future endeavors without even realizing, like you say, sometimes you're just doing it in the heat of the moment without realizing you're again and again trying to focus on that.
So my advice for parents and things like that, I mean, like even my kids, go and do sport. Do. Forget about study, sport.
It's a good outlet. Yeah. Sometimes, it's always good to have a goal, but I think after a while, if you're stuck in it without having something to take your mind off of it, like swimming's very much a meditative thing as well. You're constantly just thinking, breathing and that sort of stuff. But it does take your head out for a little bit to be able to relax as much as you are physically working yourself out, but you get to like have a little bit of a think as well. That's excellent. I love the way in which you were able to pull that into your work. I would love to find out how you went from Sri Lanka to start studying in oceanography. I guess what was the beginning? What brought you into that field?
Well, I told you I wanted to become an oceanographer, right? And there was no universities or any expertise in Sri Lanka. So basically had to look overseas. And then I looked at, I remember applying for universities. I went on a big swimming tour to China. And then when I came back, I had all these prospectus from the universities I wanted to go to. And there was only one university who did the undergraduate degree in oceanography in the UK. And as soon as I looked at prospectus, I said, this is where I wanted to go. So I went there and I lived there for 12 years.
Oh, wow.
I did a bachelor's, master's, PhD, and a postdoc.
Do you feel like living there for 12 years, you started to love a different type of ocean, I guess, the landscapes and things like that?
Again, you don't actually think about that. Again, your mindset is to actually do what you wanted to do. Everything else, the environment, you get used to it. If it's cold, Swansea has one of the largest tides in the world, right? So 10 meters, which means that you can only go out, here we actually just go, we go for a swim now. You can't do that. If you go at low tide, the water is 2 or 3 kilometers out. So, when you go out in a boat, you have, everything is there. So often you would get up at 2 or 3 in the morning in the middle of the winter and go out in a boat. But you have to do it. You now actually think about, I don't like this or whatever. It's something you had to do.
Yeah. As you start studying these different fields, like you said, it's just one of those things you would go out there at 2 a.m. and you would get all this data and that sort of thing. Back then, did you feel like the way in which you were collecting this data, was there any inkling that there was any kind of technology at that time that would help assist when you were collecting this data? So things have changed.
It's, when you actually look back in some of the technology that I used there, I'm still using, right? So, in different parts. But you actually never looked into the future. The other thing I should also say is that, I made a sacrifice to actually go to the UK. My father, being a geologist, scientist, didn't get enough money. So we had to pay. So he basically had to resign his job and move the whole family. So he got a job in Cyprus. So my family and everybody basically moved to Cyprus for me to go to university.
Wow. Good dad. Good family, really. It's the whole family, right?
It's a whole feature of that. And then when, but the good thing is that it was one of these similar to United Nations type of a job. And so they pay for the kids till they were 21 to go to university. So after you got 21, you're on your own again. Right. So then I didn't want to put the burden again on my parents and family, so I decided I would work. Right? So now you actually work and study. So now I'm trying to figure out what is the highest paid job that you could work at night and study during the day.
Yeah.
So it works out to be a bouncer in a nightclub.
Right, you were a bouncer at a nightclub, really?
So for 3 years, I was a bouncer in a nightclub. So in the same thing, I mean, I used to go to work, work finishes 2:33 in the morning, and often straight from work, go home, change, down to the docks to go and do field work.
Wow. Yeah, obviously, like you said, it was a job that came with great money, but at the time, I don't think you would have thought this is a dangerous job. It's like, it's a great opportunity to get things going.
I still remember the professor, typical, very English professor, and I used to come to the department, and maybe I had a few stitches on my head and things like that, and he would actually say, when Sir Arthur J. Rank established his empire, I don't think he ever thought he was going to support oceanography. So Arthur Rank is basically somebody like Rupert Murdoch at that time.
Okay, yeah.
He had films, he had all the movie theaters, bingo halls. He was, and films and whatever. So that was the big empire at that time. So he was actually laughing and saying,
You never know. You never know what your work ends up leading to inspire. So the comics that you read, I'm sure the person that put that information there was just to give you a bit more information.
I think it was just doing it's not for me, right? It was basically trying to motivate people to do that.
Yeah. Probably don't realize how much influence you have on somebody until someone tells you, right?
Yeah,
or
exactly.
That sort of thing. So when did you first get to experience any kind of supercomputing power, I guess? And where was that transition like going? But
maybe you should go back how I actually start, again, as an undergraduate. So computers were just starting, right? They were, all from the time I was doing my undergraduate project, it's about computers, right? Everything that I did. So you actually go from there, Fortran, and then just a normal mainframe. Then in the UK, they brought out this laptop. It's called the BBC.
Okay.
Right? So why it's called the BBC is that they actually have a TV program, and they designed from the TV program this computer, laptop, right? And basically that was the one which was going to go to the schools and the things like that, and you actually did that. So and started programming with that. But in those days, storage was on cassette tapes, and there's also the Commodore PET computer. And actually, in the end, what you're actually doing, even if you do supercomputers, you actually have to visualize.
Right.
So then you actually had the HP flatbed plotter. You had a pen.
Okay.
And every stroke of the pen had to be controlled by the computer. So you basically have to write your code, lift the pen, draw this line, lift the pen, go here, lift the pen, go in there. So that's how I basically started doing my programming.
I mean, it goes back to the time of trying to find out how this can help. And at the time, it probably would have seemed such a headache to do.
Now actually, in some of my talks, I actually put a old computer card. I don't know do you know what a computer card?
Is it like a punch card kind of thing? Or
Yeah. So you actually type it in, and then you actually hold a lot of these, and then you go to the computer. So you might have a stack, and you put it in there, press the button, it runs your program. That's how it sort of started.
I mean, imagine dropping one of those files. You'd have to go back.
Nightmare.
I'm sure.
Absolute nightmare, to be able to do that. So that's, so there was no supercomputing or parallel computing. So when I came to Australia, that was what I actually was striving to do. So it took me like 2 years to raise enough funds to actually buy a Sun workstation.
Okay, this is it, and
just a standalone, but it had more computing power than anything. So that basically was the main part. And then we had, I can't remember what company it was. They gave a good deal. Ultra super fast computer. Comes back and good, this perfect. You got that. Then there was a company in California who actually gave us they called it a supercomputer, but it wasn't that much fast. Right? So we had that, but I never actually used it. So it was, up until IVIC came along, it was mainly running on the Sun workstation.
Okay. Your go-to machine was the Sun workstation that you've been used to probably for, I guess, a few years. You were using this?
Yeah. Maybe 5 or 6 years.
And then IVEC comes along. What's interesting to me is the fact that you have this mode of study, but then you also have to start learning programming and understanding how to use these machines to try to do the tasks you're hoping for them to do.
Yes and no. The interesting thing, I never ever have any formal training in coding. So all self-taught. Right? So it's basically running Fortran programs. And then the next one that basically I had, the first week I was at UWA, there was a postdoc. And she came and said, "Oh, Chari, you know, I'm so-and-so." And said, "Look, my brother is developing some software and he's got this little company, but would you actually consider buying this software?" And so she gave me 2 5.25 floppy disks.
Yeah.
And I said, fine, let's have a look. It's MATLAB. That's for visualization.
Okay.
It's in there. So you have different components in a sense. So if you're running a Fortran program to actually do anything, you got to compile it and then you run it. There's a whole lot of steps. But in MATLAB, you can do this straight away. Right?
Oh, okay.
But it is very limited in terms of memory and how big that you can do things in there.
But that would have been a big change for you going from one way of processing what you would hope to do to this MATLAB, which was visualizing that really quickly. It started to improve your work. Yeah.
Came here, I started doing that.
Yeah.
So, but that was till I actually got used to MATLAB. I was because in program you use what you actually know and what you're comfortable with and what your knowledge is. Yeah. So the first few plots, the first few papers I wrote was basically these line plots with a flatbed plotter. Right? And then I went to MATLAB and then started changing the way you create the plots. And
excellent.
So when you go to supercomputing as well, right, the way that I have worked is that you do the big number crunching on the supercomputer, but you do all your visualizations on MATLAB.
Okay, right, yep.
So it's very different to some other people will do, but the way that we have worked and I have worked is that way.
Yeah. Is that how you felt comfortable, I guess, using visualization, is because MATLAB had this way of being able to present this data the way you wanted?
I was familiar with it.
It was your comfy space.
I can do anything with MATLAB.
Yeah.
Right? I have a picture in my mind. I can actually get it done in MATLAB.
Yeah.
But in the computing power that I have, maybe I don't actually have the space and the memory to be able to do the big number crunching. So you do the number crunching in the supercomputer, and then you basically do the visualization and the summary plots and things like that.
Yeah. Technology always seems to be a way for us to expand our sort of a view on how we want to capture something. So you might be limited to, say, data storage or these sorts of things. And then along comes a new piece of tech that says you can do 30 times the amount of processing that you would want to. Yep. Does that make you, when you're trying to work something out, have to step back and go, okay, maybe I should be asking a different question or a bigger question?
So, I mean, it's also how you evolve. I mean, the lot of people really didn't like MATLAB because it's commercial software. You need to pay a big licensing fee, and so basically that's how Python has started.
Right.
And it's the same as Windows and Unix. I don't want to learn Python. Well, it's a new language. Why? I don't really want to do something and spend my time learning something. I have enough people who work for me and said, "Oh, Python is more efficient to do that." I said, "Can you please do this to me?" And then it can be done. So I still do a lot of MATLAB programming. I mean, people still get amazed. They walk into my office, "Hey, are you programming?" I said, "Yes, of course." That's sort of the thing you like to do, right?
Yeah.
So I'm still a lot of hands-on and virtually 80 to 90% of the figures that I use in my papers, I make it from scratch, right?
Excellent.
So a lot of people at my sort of level will not do anything like that, in the sense. So the technology does improve, but in my case, I stay with what I'm comfortable with.
Mm-hmm. Yeah, that's it. You don't have to join the crew and join every single new flashy bells and whistles thing. If you know how to get an answer that you see in your head, sometimes it's good to go back to the machines that work well. Okay, I want to check to see how you went from using MATLAB and then going into supercomputing. How did that help your work when you started to find out that you could use this power to do all the number crunching before you would visualize it?
In all of this, you basically have, so what I do, to give you a sort of an example, we would have a area of the ocean, let's say the coastal waters of Perth, let's say from Fremantle to Yanchep or whatever, and then you run this, model, computer model. So you basically, these days they call it a digital twin.
Okay.
So basically, you're simulating the ocean in the system. You're limited by two things. How fast is your computer to actually do the scaling? So what we're doing, just like you do on a TV, it's a pixel, right? So we're actually dividing the ocean into little squares or rectangles.
Okay.
So how many rectangles you can have in that system and how long can you run the system? Is the ones which actually depends on your computing. Right? So it's always a balance. So you pick your resolution, we call that, based on how long you want to run. I remember in one of the students who was actually running it, he was looking at rip currents. Right?
Okay.
And we were selected 2 meters resolution. But when we actually put it on supercomputer, it took 4 times real time to run 1 hour. So 1 hour of simulation would take 4 hours of supercomputing time.
Right. Okay.
Right. So, but that's what we wanted. At that time, nobody's ever done that before, right? In the world.
Right.
So that high resolution in the system. And so that's basically an example. Photonics probably now do it a few seconds.
Probably.
So that's the sort of the advances. So that allowed, so those days when we started, even with Carlin and Cognac, we could basically run for a few weeks. Now we're running 20 years.
Yeah.
And we're running whole of Australia for 60 years. Right? So we're reducing that resolution, but also extending. And that we can actually do that because of the supercomputing. Yeah.
Does that continually blow your mind knowing that you can extend these sorts of projections way further than you ever did, say, 5, 10, 15 years ago?
The thing is that what you do is that rise to the challenge. Right? So rise to the challenge in the sense, okay, I have this computer, right? So those days, one model run on my son's workstation for, let's say, 10 days would take about 5 days.
Right.
So you actually run it in the background, in your office in the corner, it's churning away. You're doing something else till your simulation finishes. Right? So, but that's only the thing. And you say, well, I would like to do higher resolution because the higher the resolution, the more things that you learn.
Right.
So this is what basically brought with the supercomputing. And as the computing power increased, we also increased. We reduce our resolution. We simulate a bigger area. We can run longer simulations.
Do you remember the first time you were able to increase that resolution or just increase the way you were studying something and just how that felt to sort of see your work, the potential?
Absolutely, because we then started learning more about the ocean, how it works, because we have the higher resolution. And definitely.
Supercomputing in the way that these machines continually evolve and get bigger and that sort of thing. What I'd love to find out from you is because we have these sorts of processing power with supercomputers, is there sort of a worry that if we didn't have access to those, that we wouldn't be able to do the kinds of challenges that we need to do?
Definitely. It's not only we're talking about the supercomputing, but it's about what we call parallel computing. So we actually take the piece of the ocean and we run it. Right? That's what I did with the single processor Sun type of things that we're looking at. How small, how high resolution can we go? What big domain can we have? And how long can we run? Right? So those are the three main things in the ocean that we can do. So now imagine that we actually have the Sun workstation would run very low resolution, let's say, for the Perth area. We're running that resolution to an ocean which extends from Singapore to beyond New Zealand. So that
Big space.
a big space. And for 20 years or longer.
Yeah.
When we could only run for about 10 days, which would take 5 days. So that is the advances and the advantages that we basically have. And it allows us to do so many things, find so many new things about how the ocean works, which is basically what I do. So, I can look at a satellite image and say, well, that's interesting.
Yeah.
How can we explain that? So, we said that I was a physical oceanographer, but I also talk about, I'm a process. So I look at processes, so how does the ocean work? But computing is not the only thing, right? So the computing also has to be supplemented by going out on ships and collecting data on the real ocean. So that's another completely different part. So my research in the ocean basically has three components in there. So I call them sort of the field measurements, numerical simulation, which is the computing, and then satellite remote sensing.
Okay.
So think of the ocean as a jigsaw puzzle.
Okay.
But those pieces are what I just said. Right? So one part of information will come from the computing, some part will come from the ocean, some part will come from the satellite. They're all complementary because they give different things. And then my job is to actually put them all together and tell a story.
Just jigsaw puzzling every day.
Yeah, exactly. Exactly. Yeah.
Do you feel like it's been really helpful? It's just out of curiosity as well, because of all the data you've been able to collect. Say you ran in Australia for 60 plus years, right? Yep. How helpful that's been to have that access as well in that continual collection of data.
Well, this is the 60 years of not actually field data. This is computing
simulation
data, right? So 60 years simulations only because some of the tidal cycles are about 20 years. So you need to have 3 of them to actually do that.
Okay.
So we run that. And we ran it to actually looking at the extreme water levels. So anywhere around Australia, we can go to the website and actually say, well, okay, this is the maximum water level we will expect at this particular location. And the other part that, in the field data and all of the thing is that we make that data available freely to anyone. So we'll have a website which will deliver the data and off we go.
What really makes tackling those really tough challenges is being able to have access from different players as well, I imagine.
Yeah.
I would love to talk about your gliders and the kind of work that comes from that as well, because like you said, there are some components. There's the computing and then there's the satellite as well. And then there's the physical having to go out there again.
Yep.
And how, I guess, the technology in that space has made it, I guess, safer for you to also get this information, because as you said, the ocean can be quite a rough place to be.
Before IMOS, which is the Integrated Marine Observing System, which actually funds the gliders and things like that, just go out on the boat, go out on a ship. In fact, this month now, 25 years ago, we did the first ever research voyage.
Really? 25 years ago?
Western, Australia, even now, has only one ship.
Okay.
and it basically goes around. So you got once in 2 or 3 years or 4 years chance of getting ship time. So it's competitive. You write a proposal and you get it. So we had 12 days, and we basically collected data. So that was the first time. We collected, let's say 230 stations. That means the ship will go, stop, and we lower an instrument 2,000 meters, comes back, that's collecting the data. 2 hours sailing to the next one, do the same thing. Right? So you do that and you sell. Now the gliders are autonomous. They actually do that. Will actually do in that same 13 days, it will cover 500 kilometers or something like that.
Wow.
And also will collect something like 3,000 dives.
That's huge.
So remember I told you about the resolution, right? So you can have high resolution and temporal. Right? Gliders do exactly the same compared to a ship.
Right.
Much higher resolution, much more data, and a lot more. And the other thing also is that in a ship, when the weather gets bad, you've got to come back ashore. Gliders out there. So it's collecting very different types of data.
Wow.
So there's a parallel in them in terms of before and after.
Yeah. I think that's the what's so exciting to hear about that kind of evolution of these technologies as well, is because you are getting data that you probably have never seen before. It's probably going through certain places that you've never...
we're collecting, at the moment, we're actually collecting data from the Gulf of Carpentaria.
What's that? What's that?
Up in the North Cape York Peninsula.
Okay.
There's a town called Vipa that's we actually deployed. And so we're collecting data. And the thing with the gliders, in the same way, in the very high resolution, both in time and space, we're finding things that we never, ever even thought about.
Really?
Because we missed them by having that ship-based, very low resolution data. So that's amazing.
It's incredible to hear that. I love hearing the fact that there are certain ways in which, you're so used to a way in which you can collect data, and now as things change, you start going, wow, well, we didn't realize about this. Maybe we can bring that into our next project or continue that.
Yeah, but so we find things from the gliders, and then the gliders are not there all the time. So how do you fill the gaps?
Oh,
Supercomputing.
I would say it's a computer.
Exactly. Right? And then so you understand these processes and said, oh, look, this is happening. So one of the main things that we found with the gliders is what we call dense shelf water transport.
Okay.
So what happens in Australia mainly is that during the winter months, there's a lot of heat loss from the ocean, land as well, but from mica. So the coastal waters becomes cooler than the offshore waters.
Okay.
But the cooler water is more dense. So it sinks and goes along the seabed. So that's how it actually takes the water away.
All right.
We never knew this was happening. So everywhere we put a glider, in anywhere in Australia, we found this process.
Oh,
right? So it's so unique in that sense. So now we actually want to know, well, okay, now can we simulate it? Can we put it in a computer? And we actually take that. Yes, we can. And then we actually say, well, how does it change? How does it change to year? Right? So we've heard of El Nino and La Nina. How does these systems change in different locations for these different forcings?
Once you discovered something like that, did it really shift the way in which you were hoping to, I guess, study a particular project and thought, well, moving the gliders a bit too much?
So this is the sort of, it's a different paradigm.
Okay.
So with IMOS, which I sort of part of the team which set it up, in terms of write the proposal and things like that before it started. So the idea is that we will have a global an observing system.
Okay.
So the ocean observing system. So you actually put instruments there and you actually make measurements. While doing those measurements, you may find lots of very interesting processes. And then you actually write about them.
Okay.
It's very different to say, okay, here, I'm going to I never actually wrote a proposal to say, I'm going to look at dense water transport. This is my aim. This is what I'm going to do. This is, the idea of writing a research proposal. Never did that.
Right.
The data is there. And it's always coming in. So 20 years later, we're still doing new things happening. So that's sort of the different parts on how things have changed. So in the before, we would write a proposal on the ship, right? These are the processes we want to look at. Sometimes you didn't know they exist. So it was actually sort of, you hedge a bet. If the conditions were right, you would get this, that, and the other. But now it's there all the time.
Can you remember, I guess, one of something that really surprises you about the ocean since you've started that, I guess, over your time, you've been like, that is something that I don't think that we've really realized about our oceans up to this point?
Well, I talk about the dense water. Right? We are unique in that way. So that's the other thing about the oceanography. If you are in Britain and people say, you're from Australia, you're upside down. Right? So my phrase is that, yes, we are upside down, but in Western Australia, our oceanography is upside down as well. It does completely opposite to anywhere else in the world. Right. So a lot of things that you would actually read in a textbook and generalize doesn't happen here.
Right.
So that's been part of a challenge to actually get some of the findings that we do to be accepted by the people who have very narrow minds in a way. No, that can't happen. Right? So you have to, it's been a challenge in that particular case to be able to do.
I think I've seen you say at one point in one of the talks online about how the Indian Ocean is the most misunderstood of all oceans.
Yeah, it's different.
Yeah.
It's different because it hasn't got a northern section. In lots of these things, in a way, I also say, is it being in the wrong place at the right time or the right place at the wrong time?
Right.
And I mean, I can actually say many examples in it's in there. So in 2004, I was on holiday in Sri Lanka and going to the beach when the tsunami happened.
Wow, you were there.
So I got wet that way. And I was the only one of the few people in the world. I mean, actually only person maybe now, but at that time, when after Japanese tsunamis, nobody's actually, somebody who works in tsunamis never experienced a tsunami. Right?
Oh, right. Okay, yeah.
So they sit in labs and things like that and do basically computer modeling. So I was actually in that system, and then, I was then nominated by Sri Lanka to be in the team which developed the tsunami warning system.
Oh, right. Okay, yeah.
So I was in charge of, guess what? Computer modeling.
It's like because you knew it? Or they were just like, we need somebody to be able to do this?
Well, I mean, they're committees, right? So you actually chair committees and you direct the committee and things like that. And, how can we actually develop the software which is required for the thing? And so you actually so I didn't actually do the granting, but also supercomputing facilities. And I can run tsunami models much higher resolution than anyone else can do. So that you do as well. So in all of this, to be able to not identify, but take advantage, right, of what you have and build on that in the same way. Why should a plane just crash off Western Australia, basically? And I'm the only oceanographer, so everyone comes to you to ask things about it. And then you said, yeah, it's cold, it's in there. And then you actually say, well, hang on a minute. We have much more skills than just saying it's cold and rough and whatever. We can actually use computing power to actually do this. So we did. Right? But nobody listened to us because what we were saying was far too fetched.
Right.
Because we said, any of these debris will end up in the Western Indian Ocean, so Mauritius or Madagascar and all of that. Nobody would say no. Australian, the ATSB, the official, they said, the debris will end up in Sumatra. So they actually told the Indonesian government to go and look for debris.
All right.
I said, hang on, that can't happen. We have these current systems and whatever. And of course, when the flaperon ended up in Reunion Island, everybody started listening to us. Pawsey rang me up and said, would you like some supercomputing time? And we will actually, so we were running it on a desktop. Again, the same, we can only do certain things. So we can, So they, Pawsey gave us a programmer and computing time, and we do all of these pretty cool simulations. And then when we were just about finishing those simulations, this person comes, visited me from the US. He was a lawyer, and he said, "Where should I go to find debris?" And I said, "Well, look, this is where you should go." And so off he went, and he found debris in the places that we predicted.
Wow.
He's found 54 pieces.
54 pieces, that's a lot.
And most of them from the areas I told him to go. And that comes from the simulations that we did.
It's like late term vindication, but still, you just hope at the time that you were like, we understand this space, we understand these waters, please have a listen to what we're trying to say about it.
Yeah, I mean, it's sort of interesting. In the next 2 months, they're going to go out to look for it.
Okay. Oh, they're going to go back and look for it again, really?
Yeah, that's right. So fingers crossed.
Here, please take this PDF and read it for a little bit. So is there any kind of, collaboration with the work you've done in the past for something like that, if they were going to go look out, or they got
the thing is that, it's happened. Right? Nothing's changed.
Right.
You can't change anything which happened in, 11 years ago, 2014. So, I mean, we haven't done anything since 15 when we did the supercomputing stuff, because there's nothing else to do.
You did all
other than going physically go and finding things.
Yeah. It's incredible to think that there was a time in which, the kind of searches, I think I've seen it in some of the videos that you've talked about, the way in which they were looking at particular zones, like zone 1, 2, 3, and then we'd go back up. And what you were able to do was a lot more detailed and be able to go well, this is the sort of 2 years of is it current flow that you were able to take that data?
The current flow and then the current flow will actually use the debris.
From the learnings you did from the currents that you did there, were you able to take that kind of studies that we were using and put it into different projects you were working outside of that?
Other way around.
Other way around, really?
Completely the other way around. That's what I'm saying. We, rather than saying, hang on, it's rough and it's windy and it's big waves and it's cold down there, we have the skills to actually trace some of this stuff. So that's basically what we have been doing. And we had all that expertise long before MH370 came along.
You were already in the business of that.
We were also, it was basically taking that expertise. So, for example, so in all of this, what we're doing is that we are basically in the computer tracking parcels of water, right? That parcel of water may have fish eggs, it might have lobster larvae, it may have dead seaweed, it may have aircraft debris, it might have plastics, it may have turtles. So anything is the same, but we are actually tracking that. So how you track it depends on what you're tracking, but in terms of the principle, it's basically the same. So we had a big project down in Port Geographe in Busselton, where there was a problem with seaweed, which was basically accumulating. It was smelly. It was horrible environmental disaster. So the government came to us to actually redesign and to solve this problem, which we did. And the government spent $27 million, which actually based on our recommendation to remodel the system.
Wow.
So we had all of that expertise, right? And so MH370, no problem. We can do that.
The work that you get to do in the future, you have no idea how the applications can be used for it.
But it's the same thing as people say, sort of they say, you have an uncanny thing to actually look at that and say, we can do that, or this is what happens, and things like that.
Is there anything you've been working on lately or something that you're hoping to do in the future that you're really excited about?
My idea is to see how I can consolidate a lot of knowledge in here and how can I actually convert it. But I still haven't got to the mindset to actually be able to do that. The way, as I said, because the oceanography is upside down, I have the opportunity to find new things, pioneering things I can discover. In a lot of them, it's actually the unique nature of WA. That's what actually allows you to do things. That, again, it's part of mentoring, teaching, giving part of that knowledge into the system.
Well, I'd love to be able to hear as well, because I know you've done work in terms of not just predicting extreme weather patterns around Australia, but also flooding, I believe it was. You have some pattern or some...
It's coastal flooding.
Coastal flooding.
Yep. Yeah. So it's basically, that's the same thing with the sea level.
Right.
So in terms of the extreme sea levels that we've been talking about. So the other thing to actually put the two things together, so we talk about tsunamis, and most people think of tsunamis originating from earthquakes.
Okay, right.
There's another different types of tsunamis, which is called meteorological tsunamis, and they're generated by atmospheric effects, mainly thunderstorms.
Oh, really? Okay.
So again, guess what? Southwest Australia is a hotspot. So we get many, many of them, a lot more. And we call them meteor tsunamis, are much bigger than the seismic tsunamis. And we may have 10 or 20 in a year.
Really, that
many? Don't realize.
Oh.
So these things are common, and we've had problems in Fremantle Harbour where boats actually, ships have come ashore, broken their moorings and things like that. Being right placed, everything happens. So, and I said that during the seismic tsunami, I was in Sri Lanka. So the day before the Rodney swim that I was doing, I said, obviously, have to have a look at the weather forecast. And they were predicting thunderstorms. Oh, hang on a minute. There's going to be a meteor tsunami. So sure enough, there was while I was swimming.
Wow.
So I'm the only person in the world who has swum in a seismic tsunami and a meteor tsunami.
That's a hefty CV of tsunamis you're collecting here. Did you?
Yeah, but
sorry.
Do you see what I mean?
Yeah.
Right place, wrong time, whatever.
Just being able to do that challenge of the swim in itself is quite big, but then thinking as you're going into the water that the waters might be able to do.
I mean, in deep water is not, because I did it in a sort of a relay in a team. So the only I only knew it was in a meteor. The tsunami was there because I saw the thunderstorm. But then because you have to get into the boat to have your rest.
Yeah.
But getting onto the boat, because the boat was going up and down and whatever, it was hard. But it was only for about 10, 15 minutes, and you know that, right?
Yeah.
And so you can tell the others, don't worry, this is it, and you calm down.
I was about to ask, did you tell all the swimmers as well? I was like, something's coming up. And like, you're just trying to get me riled up.
But then, again, something you learn, right? In tsunami, in Sri Lanka, I kept telling people and said, hang on a minute, it's come and gone. The tsunami lasts 10, 15 minutes. That's it. It's come and gone. And then I went to this beach, and then this huge tsunami comes. So I was now thinking, then I'm actually driving back, and people were running. What is going on? Right? This is not the tsunami that I have learned and researched and things like that. So I managed to get a tide gauge established, because once visiting Sri Lanka, I was telling everybody Sri Lanka is one of the luckiest places on, because they don't have global warming. You say, what do you mean? It says, well, you don't have any sea level rise. And people say, what do you mean? He said, well, you don't have a tide gauge. You're not measuring. So how do you know?
That's fair.
So, and then when I came back, I basically contacted some of my colleagues in the US, and they agreed to put a tide gauge there.
Yeah.
And that was established sort of 2 months before the tsunami happened. It's one of the few tide gauges which is operating to record the tsunami. Right?
What timing?
What timing? Again, initiated by me again,
Right.
And what I actually found out was that those big waves were coming. The waves had gone past Sri Lanka, hit Maldives, got reflected and coming back.
Oh, okay.
So that's the first time that people have shown how these, and then we looked at Western Australia, that the biggest waves in Western Australia came 18 hours afterwards because they went all the way to Madagascar and came back.
Wow. It's interesting to be able to tell people that too. It's like, where did this come from? Well, actually, we can show you. This is how it's
exactly. Spread. The tide gauge is basically a tube, right? So what you want to do is to actually not have waves, right? Because you're actually measuring the mean sea level.
Okay.
So you basically have a tube with a little hole in the bottom, and you have a float.
Okay.
So when the water level goes up, the float goes up and down, and then the old way was to actually connect that to a pulley, and it'll actually do an analog trace.
Oh, okay.
So that's the old one.
Yeah.
So now rather than the float, they actually have a radar system. So it basically measures, just like an echo sounder, the height of the water level inside that tube.
Again, another change in the technology that just makes it a bit more accurate.
Yeah, absolutely.
Yeah.
Again, see, before the analog traces were digitized every hour, which missed everything which happens in between the hours. Right?
Right.
So now we are measuring at 1 minute or twice a second. So you're seeing a lot more different things.
That's a huge change in resolution, right?
Yeah. But it's all it's all development, right? Because of basically technology, mainly memory, right? Battery, and different way of measuring things.
Is there any other projects you'd love to talk about that you're in at the moment that has utilized supercomputing in any particular way?
When IVEC came along, right? So there is one part that we talked about in terms of the rip currents. Right? It's a fantastic study in terms of we could never have done that to understand how these currents form and where they form and how all of that was actually done with this super study in terms of, right? People are still doing that same experiment now, 25 years later. Right. It's because not many people have the access that we've had to supercomputing. But you can see that that's the same thing that I was actually saying, right? I'm lucky to have Pawsey and IVEC, right? If I was somewhere else in Australia, I wouldn't have that, right? Or in any other country. It's having that facility, and then it's not only having the facility, but to actually take advantage of it. So then we actually we were starting, so in Western Australia, we're really interested in the Lewin current. Right?
Okay.
So, which is what we call a anomalous current, which actually brings warm water from the equator down to the southern latitudes.
Okay.
In other countries, it's the other way around.
Oh, right.
Got cold water going on. So that's why it's different. So we're trying to understand. So I had students who were basically looking at, let's say, between Geraldton and Perth. And we were simulating that and to understand how this is happening. And and then we actually expanded it to Western Australia. Then we expanded to whole of Australia. Then we expanded it all the way from Singapore to New Zealand.
Wow.
And then rather than running it maybe for a few weeks, a couple of months, so those days we could run summer and winter. In between we could not because we didn't have the ability. Even with the supercomputers with like Cognac and Carlin, the initial supercomputers, they still didn't have the power. But now with Cetonics and things like that, we can run for 20 years longer in terms of the system. So all of those actually will develop in that system.
It's so huge just to think like how the potential just keeps growing and growing, and it just helps you to sort of reframe what do you want to look at now.
So it's not, again, running tsunami models to see what is the risk for Western Australia. Right? So we're lucky to a certain extent, south of Geraldton, because all the waves coming from the north gets deflected because there's a big underwater topography.
Okay, right.
Which which actually protects us. So actually to do the computing and actually show this is what really happens, it's good.
It's great. It comes in handy, right? Especially when you're trying to predict things that are happening in the future.
But the thing also is that, with tsunamis and storm surges and all of that is human safety or infrastructure. Right? So a lot of that is also got sort of satisfaction in terms of, tsunami warning, if you can save one life.
Oh, for sure.
It's fantastic in a way, but it's, when we're actually doing the tsunami thing, because, again, with all of these funding is a hard part. So many times we've been asked and says, can you put a cost on a human life? A dollar amount for a thing. It's really interesting because nobody ever wanted to, when we were doing tsunamis, wanted to put a dollar value on the price of a life.
Even if it was a scientific...
COVID, because it was so important to say how much money are you going to spend to contain this.
Yeah, you needed to prove the reason why you were doing such a focus on it. Yeah,
it's fascinating in that way.
Yeah, I would hate to be the person that put that together, and then people thinking, "How could you? How dare you?" But the understanding is we need to be able to justify why we need to do this study. For example,
So in our case, zero deaths. That's the bottom line.
Yeah, there is a continual drive for not just information, but hitting these challenges. Right, there's always a challenge to be solved.
And in often, I don't think people realize to a certain extent how much effort that goes in. Still there's challenge. So the challenges, whatever supercomputers we have, we still can't run climate models for predict what happens in 2050 or even in 10 years' time at the resolution that we want. People talk about, the cyclones are, we're going to big storms, we're going to have that, but we can't simulate that because we don't have the computing power to be able to do that.
Right. Yeah.
So there's still challenges ahead to be able to run these models at the resolution to actually resolve the different processes. So none of the climate models resolve a tropical cyclone. None of the climate models resolves the La Nina, El Nino events. We have no idea about all of this. So at the moment, if I give you the analogy, the climate models are my Sun Micro workstation.
Right.
That's the level that we are in. We are just in the place to actually do that. But this is big groups around the world trying to do things. But we're not there yet.
Not yet.
From a computing part, from the ocean and the atmosphere, that is the big challenge.
I guess
I'm not going to do that.
You're supposed to do it. No, I guess it proves that I guess it's really important for us to continually invest in these sorts of...
Absolutely. It provides answers societal questions, definitely. Yeah.
I really appreciate your time with me, Chari. It's
no problem.
Get to hear about all your wonderful adventures. I'm sure there'll be many more as well.
Yep.
But I can't thank you enough.
No, you're welcome. Thank you.
Thanks for listening in to our chat with Chari. There are a lot more stories for us to share with you, and we can't wait to release our next episode. If you're interested in what supercomputing can do to research, visit our website for more stories like this. Until then, we'll talk soon.